Greetings everybody to our third example of polar curves. So in this problem, what we're asked to do is to find the exact area in between the curves r is equal to 8 sine theta and r is equal to 6 cosecant theta. So let's go over to GeoGebra and take a look at what those curves actually look like when we plot them. So what we find is that our r is equal to 8 sine of theta is giving us the blue curve that we have here, and the r is equal to 6 cosecant of theta is giving us the straight line. And so when we're asked to find the area, exact area inside of the circle and above r is above the line, we need to find our intersection points to find our limits of integration. And so once we do that, we can find that algebraically, really just by equating the two radii. So if we have r is equal to 8 times the sine of theta, and r is equal to 6 times the cosecant of theta, then equating those two, we have 8 sine of theta is equal to 6, and cosecant we can write as 1 over sine. And so what this gives us is an equation where we have sine squared of theta is equal to 6 over 8, or our 3 over 4. So taking the square root of both sides, we have solutions plus or minus root 3 over 2. And so for the values that we actually have from that, kind of thinking of our circle, we're going to have solutions in all four quadrants where our reference angles are all going to be the same. And for those values, are going to have a sine of root 3 over 2, and so our reference angle for all of our solutions is going to be just our pi over 3. So we're actually going to have values for theta being a pi over 3, 2 pi over 3, 4 pi over 3, and 7 pi over 3. But now when we go to actually plot our circle, if we're graphing that circle, then what happens, we only need the intervals in between 0 and pi to actually plot the circle. And so what that tells us then is that our two intersection points are then going to be at pi over 3 and 2 pi over 3. So this is going to give us the limits for our integration. So now if we're wanting the areas that are above the line but inside the circle, then we're really talking about these two areas here. And so our integration will be the difference of the areas. So for the area inside the circle, what we have is an integral from pi over 3 to 2 pi over 3 of our 1/2, and then our radius for our circle was going to be 8 sine of theta squared d theta. And then for that, we're then subtracting the area under the line, which also on the same limits from pi over 3 to 2 pi over 3 for 1/2 r squared. For that one, we have 6 cosecant of theta squared d theta. So now here's our integration that we need to evaluate. So then for our first integral, we can just use our power reduction identity. So we have our pi over 3 to 2 pi over 3 of our 32, and our sine squared becomes a 1/2 minus a 1/2 cosine of 2 theta d theta. And then for our second integral, well, our cosecant squared is really just going to look like is really just the derivative of our cotangent squared. So we have an integral of plus 18 times cotangent squared of theta, or cotangent of theta, sorry about that, cotangent of theta from our pi over 3 up to 2 pi over 3. So we have a 16 times theta minus a 1/2 sine of 2 theta with limits between pi over 3 and 2 pi over 3 plus an 18 cotangent of theta running from also pi over 3 to 2 pi over 3. Well, plugging our values in, what we find for the first integral is that a 16 pi over 3 plus 8 times the square root of 3. And then for our second integral, what we have is an 18 times a negative root 3 over 3 minus a root 3 over 3. And so what this gives us as a final answer is our 16 pi over 3 minus 4 times the square root of 3. So I hope this example has been informative, and I will see you guys in the next one. Take care.